Imagine you're building the online booking system for a movie theater. The screen shows a grid of seats available in green or taken in gray. Multiple readers checking availability. Hundreds of people can open the app and look at the seat map at the same time. They all see the same available seats. Reading doesn't change anything. So it's completely safe to have unlimited concurrent readers. That's the read lock. A single writer booking a seat. Now one person clicks on a seat, let's say E5, to book it. While the system is updating that seat's status from available to taken, no one else should see an outdated or half changed state. So during this brief write operation, other people trying to read that specific seat or the whole row must wait until the write finishes. No other writer can book the same seat at the same time. Java gives us ReentrantReadWriteLock. It has two separate lock objects, a read lock and a write lock. Multiple threads can hold the read lock simultaneously, but only one thread can hold the write lock. And when it does, no read lock is allowed. Here is typical usage wrapping a read write functionality to make it thread safe for many reads and writes. First, acquiring a write lock ensures exclusive access. And here we have our shared resource, which is a counter, a simple integer that multiple threads will read and write. So here we increment the value and at last we unlock it in finally block, which prevents deadlock if exception occurs. And this is the read lock. We first acquire it, multiple readers can hold it simultaneously, then we print the current value and we unlock in finally block. Now a natural question from this is, why do we need a read lock at all? Why not just let readers access the shared resource without any lock? Because without a read lock, writer could modify the shared resource in the middle of reader's iteration. The reader might see stale or corrupted data. The read lock blocks writers, ensuring a reader sees the consistent snapshot. The interaction between read and write locks allows for a number of possible implementations. Some of the implementation options for a read-write lock are: first is a release preference. So what does that mean? When a writer releases the write lock and both readers and writers are queued up, who should be given preference? Readers, writers, or whoever asked first? Second, reader bargaining. If lock is held by readers but there are waiting writers, should newly arriving readers be granted immediate access or should they wait behind writers? Allowing readers to bark ahead of writers enhances concurrency, but it has a risk of starving writers. Third, reentrancy. Are the read and write locks reentrant? Fourth, downgrading. If a thread holds write lock, can it acquire read lock without releasing the write lock? This would let a writer downgrade to read lock without letting other writers modify the guarded resource. In meantime, upgrading. Can a read lock be upgraded to write lock in preference to other waiting readers and writers. Most read-write lock implementations do not support the upgrading because without an explicit upgrade operation, it is deadlock prone. If two readers simultaneously attempt to upgrade to write lock, neither will release the read lock. So let's see how reentrant read-write lock is implemented. Firstly, talking about release preference and reader bargaining. So reentrant read-write lock supports fairness. In fair mode, if writer is waiting, no new readers can jump ahead. That prevents writer's starvation, but it can reduce throughput. In non-fair mode, reader can bark, which may starve writers under heavy read load. Also, you can downgrade from write lock to read lock, meaning you hold the write lock, acquire the read lock, then release the write lock. This allows you to modify data, then continue reading without letting other writers in. And last, upgrading. Upgrading from read to write is not allowed. It would deadlock immediately because two readers trying to upgrade would wait forever. Read write locks are great for caches, configuration data, or any read mostly scenarios. But do they still cause readers to block each other? No. Multiple readers can run at the same time, which is the whole point. But there is still a cost. Each read lock does an atomic increment of reader count, which causes the cache contention on multi-core systems. For extremely heavy read loads, that can become a bottleneck. So what if I told you there is a lock that lets you read without any blocking, no atomic increments, no contention, and only checks later if write sneaked in during reading? That's not magic. That's stamped lock, and it's optimistic read mode. This is where things get really interesting. Let's dive in. Stamped lock. Stamped lock arrived in Java 8. It has three lock modes. The write lock, which is exclusive access to modify shared resource. Pessimistic read lock, like reentrant read-write lock. It assumes conflicts are likely. Someone might modify this data while I read, so I'll lock it first. And third is optimistic read lock. It assumes conflicts are rare. Probably no one will modify this data while I read, so I'll read without locking and check later. This is something no other Java lock offers. The big difference in stamped lock is it is non-reentrant. If thread that already holds the write lock calls write lock method again, it will deadlock itself. That's a sharp edge. You have to be careful. Second, it has no condition support. You can't call await or signal method. We'll see why that matters in a bit. And third, every lock acquisition returns a stamp, a long value. You must use that stamp to unlock. Think of it as a valet parking ticket. You give the ticket and you get your car back. Lose the ticket, you are stuck. Same with stamps. Lose the stamp or forget to unlock. The lock becomes permanently locked. No get owner to save you. So finally block is absolutely mandatory. So what is a stamp really? A stamp is not just a random number. It is an encoded snapshot of lock's internal state. Internally, stamped lock stores a single long called state. It has three parts: a version number in high bits, the write lock bit, the 8th bit, which value is 128, and the reader count in the low 7 bits. When lock is first created, the state is origin, that is 256, which means version is 1, no write lock, 0 readers. When you call the read lock, the reader count increments and the return stamp includes the new count. And when you call write lock, it adds 128 to the state, setting the write bit. And when you unlock the write, it adds another 128, which flips the write bit off and it increments the version. So every write cycle bumps the version by 1. Let me show you how to use stamped lock and how the stamp gets updated. So when we first create a lock, the original stamp is 256, that is version is 1, no writer, no reader. When you call write lock method on this stamped lock object, it adds 128 to the state, setting a write bit. And in finally block, when you call unlock write method passing the same stamp, it adds another 128, which flips the write bit off and increments the version. And hence now the version of stamp is 2. And here is the example of pessimistic read, which blocks if writing and allows multiple readers. So when we acquire a read lock, the reader count gets incremented. So now version is 2 and the stamp is 513 long. And when we unlock the read with the same stamp in finally block, the reader count gets decremented. Now the stamp is 512, but the version is still 2. So make a note here. Write lock adds write bit, that's 128, and unlock write adds another 128 bit again, which toggles the write bit from 1 to 0 and increments the version in higher bit. Read lock, on the other hand, increments the lower 7 bits, that's a reader count, and unlock read just decrements the reader count. During unlocking, the stamp whichever we pass only needs to have same high bits, that's nothing but version as the current state. The lower 7 bits, that's reader count, can be different. That version increment is how optimistic reads work. And here is the example of optimistic read, which is completely non-blocking. You call try optimistic read method, which returns the current state. It's not locking, it's just returning the current state. Then you read the data, then you call validate stamp method. Validate compares the version part of the stamp with the current version. If no write lock happened in between, the versions match and the validation returns true. You have just read without ever acquiring a lock. That is insanely fast. Else, you fall back to pessimistic read. You acquire a read lock. The stamp's reader count gets updated. That's why stamp is 513 long. And finally, you unlock with the same stamp. The reader count gets decremented. This is slow but reliable. This is the optimistic read pattern, where you optimistically assume no write will happen. In read heavy systems, that is true 99.9% of the time. You get lock free reads. Benchmarks show stamped lock can be 3 to 5 times faster than reentrant read write lock on read heavy multi-core systems. Why, you may ask? Because optimistic reads, what we have just saw, don't modify any shared cache lines. So there is no atomic increment of reader count as we have seen in reentrant read write lock, and that's why there is no contention. Lock conversion. Stamped lock also supports lock conversion. For example, you have an optimistic read and you want to write only if a condition is true. You don't want to release and reacquire. That creates a race window. Instead, you can use try convert to write lock method. Let's see how. Step 1. Take an optimistic read stamp which never blocks. Then loop over the condition which may change after validation failure. Step 3. Try to upgrade optimistic stamp directly to write lock. So here we pass that stamp to get a write stamp. If it is not equal to 0, that means upgrade succeeded. We now hold the write lock. Replace the stamp with the new write stamp, perform the operation and return. Done. Lock will be released in finally block. But if upgrade is failed, that means write stamp is equal to 0. This can happen if a writer intervened or optimistic stamp is stable. You fall back to acquire write lock explicitly, and this will block if needed. Note here, we must reread the value. After obtaining the write lock, because this value might have changed. But since we are in this while loop, we will anyway recheck the condition at top. So we just continue here. But what if we acquire the read lock here and the condition also passed? What happens if we call try convert to write lock method again with the write lock stamp? We know stamped lock is non-reentrant, meaning you cannot reacquire the write lock a second time via write lock method. That would deadlock, correct? However, this try convert to write lock method is not an acquisition, it is a conversion. If a stamp you pass already represents a valid write lock stamp, that is current thread holds it, the method simply returns that stamp unchanged. Understood? And finally, here we unlock with the final stamp, which could be the optimistic read or the write stamp. In this pattern, you try to convert your optimistic stamp directly to write stamp. If it succeeds, you are now holding the write lock without ever having released anything. If it fails, you fall back to acquiring the write lock explicitly. This is safe because stamped lock is not reentrant. You never hold two locks at once. So what happens when readers meet writer? A common scenario, thread R holds a read lock. Thread W calls log.writeLock method. What happens in that case? Thread W blocks immediately because at least one reader is active. But here is the important part. Once thread W is queued, the new readers that try to acquire the read lock will also be blocked. This prevents writer starvation, something that can happen with reentrant read write lock in unfair mode. The writer gets priority once it's waiting. Optimistic reads, on the other hand, however, never block the writers. They just take a stamp and validate later. That's why they are so powerful. Now let's see the dark side. The stamped lock is not a silver bullet. Because it doesn't track the ownership, you won't see the lock owner in thread dumps. If you get deadlock, debugging is harder. Also, if you accidentally call a write lock method twice in same thread, you will deadlock instantly. No error, just frozen. And as I said earlier, there is no condition support. So if you need to wait for a condition like buffer not empty, you cannot use stamped lock alone. You would have to build something custom with lock support API, which is error prone. That's where explicit condition comes in. Now you might be thinking, these explicit locks are great. But what about waiting for a condition like buffer not empty or buffer not full? With synchronized, we had wait and notify methods, which are notoriously tricky. The explicit condition interface fixes almost everything that's wrong with them. Let's see how. Now let's see the problem with wait and notify. Let's say you have a bounded buffer, a fixed size queue. Producers put data in it. Consumers take data from it. If the buffer is full, producer must wait. If it is empty, consumer must wait. With synchronized, you have only one monitor object. Both producers and consumers call wait method on the same object. And when consumer takes an item, it calls notify method to notify producer that the buffer is not full anymore. You can put an item in it. But it might wake up another consumer because that consumer is also waiting on the same condition for the same object. That is wasted wake up. And it can lead to inefficiency or even missed signal. That's where condition helps us. A condition is created from a lock, specifically from reentrant lock or the write lock of reentrant read write lock. Why is that, you may ask? A condition requires exclusive access to signal and await. If multiple threads held the read lock, they could all be waiting on the same condition. But signaling would be ambiguous and the lock would not be held exclusively during await, breaking signal semantics. That's why for reentrant read write lock, to create a new condition, we need write lock. You call new condition method and you get new condition object. A single lock can have multiple conditions. Now producers wait on not full and consumers wait on not empty condition. And when producer adds an item, it signals not empty, waking exactly one consumer. And when consumer takes an item from buffer, it signals not full, waking exactly one producer. No more spurious wakeups of the wrong type. And here is the classic bounded buffer example. So there are two parts of it. First, the put method, and second, the take method. Let me walk you through it. In put method, we first acquire the lock. Then inside while loop, while the buffer is full, we call not full dot await method. And when a thread calls the await method, it releases the lock and parks in a waiting state. Later, in take method, when a consumer acquires that lock and takes an item from the buffer, after removing that item, it calls not full dot signal method. That signal method wakes up only one waiting producer, which then reacquires the lock. And when it will be reacquiring the lock? When consumer unlocks and the lock is available, at that time the producer will acquire it and returns from here, and then it can perform the rest of the things. Make a note here that when we call await method, we always do that in while loop and not in an if block. This is because of spurious wakeups. So what happens when two threads await and one signals? Let's simulate a scenario that many developers get wrong. Suppose two producer threads both find the buffer full. So first A will get a lock, then it checked the buffer is full, so it called await method, which releases the lock and get parked. Thread B got the lock, it acquired it, but since buffer is full, it called the await method by releasing the lock and parked itself. Internally, each one of them is added to condition queue of not full. This is first in, first out queue of threads waiting for that condition. Later, consumer takes an item from the buffer and calls not full signal. The signal method removes the head of the condition queue, say producer A maybe, and moves it to the locks sync queue, the queue of threads waiting to acquire the lock. Producer A is now in the sync queue but still parked. When the consumer calls unlock method in the finally block, the lock releases and the sync queue is processed. Producer A is unparked and it reacquires the lock and then returns from the await call. And where does it return? To exactly the same line right after the await method. It then rechecks the while loop condition. If buffer is still full, maybe due to another producer filled it already, it will call await method again. That's why the loop is mandatory. Producer B, the other waiter, stays in condition queue until another signal arrives. This first in first out behavior makes signaling more predictable than notify all method. Now, even with condition, spurious wakeups can happen. The operating system may wake up a thread without any signal, timeout, or interrupt. The official Java documentation explicitly warns about this. That's why you always use while loop and never if block. So what does condition gives us? Multiple wait sets. No more waking the wrong thread. Reacher API. Await nanos. Await until. Await uninterruptibly. Better integration with lock. You can have timeouts and interrupts together. And it is still low level enough to build things like blocking queue, which is what array blocking queue uses internally. But remember, you must hold the lock when you call await method or signal all method. Otherwise, you will get illegal monitor state exception. That's the same rule as wait and notify, and always loop on await. We have covered a lot of ground. Let's quickly recap when to use each lock. Use synchronized for simple block structured locking where you don't need timeouts or interrupts. It's safe and automatic. Use ReentrantLock when you need try lock with timeouts. Lock interruptibly, fairness and non-block structured locking. But remember to unlock in finally block. Use ReentrantReadWriteLock when you have many readers and few writers and you need to prevent reader-writer conflicts. But be aware of potential writer starvation in unfair mode. At last, use StampedLock for read-dominated workloads where you want maximum throughput. Use optimistic read as your default and fall back to pessimistic read when validation fails. But remember, it's non-reentrant. It has no condition support and stamps must be managed perfectly. Finally, use condition when you need multiple wait sets or reacher waiting API. It's the explicit replacement for wait and notify. One more thing, always measure before optimizing. Like we know, stamped lock is fast, but if your read-write ratio is 50-50, that might not help. So profile your application before optimizing. Alright, that's it for today. Go write some thread-safe code, and I'll see you in the next one. Happy locking. If you found this video helpful, please give it a thumbs up and subscribe for more technical content.